All right, welcome back. The last thing I wanted to talk to you guys about is power. Okay, and that is just the rate at which work is done. Okay, so we define it as so. We have power equal to work divided by time. Okay, so again, the rate at which work is done. Okay, the SI units are in watts or big W. And we define that as 1 watt equals 1 joule per second, okay? And we also need to note that energy is equal to power times time. Okay, so energy equals to power times time, okay? So using this information, we're gonna go ahead and do some examples because it's more helpful doing that than to just look at equations. Okay, so let me go ahead and switch over to OneNote. Discard that. Okay, and we want to first calculate the power it takes to climb stairs. Okay, so this says, what is the power output for a 60-kilogram woman who runs up a 3.0 meter high flight of stairs in 3.5 seconds. She starts from rest, but she does have a final speed of 2 meters per second. Okay, so first things first, we don't know what her work is. Okay, and we will need that in order to solve for her power, right? Because I just said power equals my work over time. Okay, so we have time, but we don't have our work. So we're gonna have to solve for that first. Okay, so remember that work is equal to our, let's see, our change in kinetic energy plus our change in potential energy, right? Or our K final minus K initial plus P final minus P initial, okay, our potential energies. Okay, so let's quickly evaluate this like we did in our last problem. Okay, if we state that this height here, her starting height is 0, okay, that means her potential energy in the beginning is just 0, okay? So remember, potential energy is equal to mgh for gravitational potential energy, okay? And her kinetic energy is equal to 1/2 mv squared. Let me just write that real quick, okay? So again, her initial potential energy, since her height is 0, is going to also be 0, okay? Her initial velocity is 0, so her kinetic energy initially is also 0, okay? So now we just have her work is gonna be 1/2 mv squared plus mgh, okay? That's what the work is. So now we can plug in our values. Work equals 1/2 times her mass, which is 60 kilograms, times her velocity, which we have, her final speed is 2 meters per second, okay, plus her mass, again, 60 kilograms, times g, which is 9.8 meters per second, squared, times her height, not her height, the height at which she moved up the stairs, and that is going to be 3 meters, okay? So, solving for that, let me go ahead and do that real quick. 0.5 times 60 times 2 squared plus 60 times 9.8 times 3. That is going to give me 1.884 times 10 to the third, okay, joules. And to solve for my power, I take my work and divide it by my time. So I have 1.884 times 10 to the third joules divided by my time, which is 3.5 seconds. And so that is going to equal about 538 joules per second, or 538 watts. Okay, so that's how much power output she does, or she produces, going from the bottom to the top of the stairs, top of the flight of the stairs. Okay, so next time, you know, you're running upstairs, which I don't recommend, you can calculate what power output you put out. Okay. All right, so let's look at the last example here. Now this one is another like day-to-day thing that you might be interested in, okay? This one is calculating energy costs. Okay, so this one says, what is the cost of running a 0.2 kilowatt computer 6 hours a day for 30 days if the cost of electricity is 12 cents per kilowatt hour? Okay, so remember that energy is equal to power times time. Okay, this is what we're going to be using. Okay, so our power, our amount of power is 0.200 kilowatts. Okay, and our time is going to be based on this. So I could put this down here. My time is going to be, let's see, 6 hours per day times 30 days. So what's 30 times 6? Whoops. 180 hours. Okay, so that's my time, 180 hours. Okay, so now for our amount of energy, we get 0.2 times 180. We get 36 kilowatt hours. Okay, so this is the amount of energy that will be output. Okay, now I want to know the cost of that. So my cost is going to be my energy, which is 36 kilowatt hours times my cost, which is 0.12 per kilowatt hour, which is going to be $4.32. Okay. So this is our cost of running a computer, which takes 0.2 kilowatts in 6 hours per day for 30 days. Okay. So this might be something you're a little interested in if you're ever, make sure that PG&E isn't, messing with us. Who knows? Okay. So that is for this example here. And then I just wanted to talk real quick about renewable and non-renewable energy resources. Just a quick idea of it, no political standpoint here. Don't want to get into that. But just to kind of give you an idea of how much energy we use and what type of energies are non-renewable. So I can go ahead and mark off a few that I know that are non-renewable. I know petroleum is not. Coal is not. Natural dry natural gas, I don't believe so. Hydroelectricity, that should be. Nuclear, probably. Geothermal, wind, solar, biomass, yes. Geothermal, biomass, solar, not used for electricity. Okay, so our main ones here are non-renewable energies. So that's just something to point out. If we want to continue our future, we should probably find things that are better. Hydroelectricity is good. That's just based for water, right? Water, the movement of water creates electricity. Like we talked about in the beginning, we have some kind of mechanical energy that then produces electricity. Okay, so electrical energy. Okay, so these things are pretty good things that we could use. Now, I don't know how much that hydroelectricity would actually produce. You know, if we did X amount, I'm not sure. But right now we're just looking at petroleum and coal as our main ones, and that those ones are non-renewable resources of energy. So just something to look out for. And this is a projection in your textbook, and it was based on data from 2011. So I mean, this could be off a bit, right? But it just shows you the general trend of the amount of energy that we consume yearly. Okay, so as you can see, it is on an upward trend. Again, it was based on data from 2011, so somewhere in here. So this is real data right here, up to here. Okay, and again, this is from your book. I'm sure that there's new things out that have this information. So it's just something that's interesting to look out for, looking into our future about renewable and non-renewable energy resources, and your book has some more information on them. I'm not too worried about like testing this on you or testing you guys on this, so I wouldn't worry too much. Just something kind of like food for thought to know about. Okay. So anyway, that is all for this module. And if you guys have any questions or anything, just let me know.